So we have seen, we have talked about DC to DC buck and DC to DC boost converters, right? Buck converter was primarily meant for reducing the voltage, and boost was for increasing the voltage or boosting the voltage. So if you have a source which is, let's say, of a higher voltage, and you have a load which requires a low voltage, then you can use a DC to DC buck converter. Similarly, if you have source of low voltage and load of high voltage, you can use a boost converter. But in certain situation, you would see that the source voltage is not constant, it varies, right? For example, you can consider solar photovoltaic panels. Now the panel voltage, maximum power point voltage, would depend on the ambient conditions, right? Would depend on the temperature, would depend on the radiation. And therefore, the panel voltage might change during the day. In that case, sometimes you may want to do a buck operation, right? And when the panel voltage is more, and sometimes you may want to do a boost operation when the panel voltage is less, so that your load or the other terminal of the converter can be maintained at a constant voltage. So sometimes you may need a buck conversion, sometimes you may need a boost conversion. So how can we do that? That is what we would see in this video. So let's talk about DC to DC buck boost converter. This is how the converter looks like. You have a load resistance, inductor, switch S1, switch S2, input source Vin, output voltage Vo. Right? Now how does it operate? When switch S1 is on and S2 is off, the equivalent circuit with respect to the inductor would look something like this. Current would, if I define this as the reference direction for current, this is the reference direction of voltage, I can see that the inductor voltage is equal to Vin, and therefore dIL by dt is going to be positive, right? When S1 is off, S2 is on. In that case, now the inductor current would continue to flow in the same direction, and therefore it would flow in this direction, and it would charge the output capacitor from the reverse direction. The usual buck or boost converter, we saw that the inductor would charge the capacitor from top. In this case, the inductor would charge the capacitor from bottom. So therefore, the voltage that will get accumulated or that will get developed because of this inductor current is going to be of reverse polarity. Right. So this is one of the key difference between the two converters which we have seen till now is that in buck boost converter, the output voltage polarity is negative. Right. So it has reverse or negative output voltage polarity, right? So now what happens in this condition? In this condition, again, I can write the inductor voltage, which is going to be minus of VO, right? Now VO is the magnitude of output voltage, so therefore I'm writing as minus of VO, right? And you can see what will happen to dIL by dt. dIL by dt is going to be negative, and therefore current would fall, right? Now in this case, you can, for example, you can visualize by drawing the inductor current waveform. S1 is on, S2 is on. When S1 is on, we associate duty cycle with switch S1. So this is D times TS, this is TS. Inductor current would rise, inductor current would fall. This is how the inductor current would look like. Now, once we have analyzed the basic operation of the circuit, we can use the volt-second law to find the relationship between the output and input voltage during steady state operation. So we can write that integral of VL dt is equal to 0, which would give us P in, which is the voltage during dTs period, plus minus VO, which is the voltage during 1 minus dTs period, going to be equal to 0. If you simplify this, you would get output voltage upon input voltage is equal to D upon 1 minus D, which is the expression relating the output and input voltage of a buck boost converter. Now, if you remember, in other converters also, there were few assumptions. Same assumptions are taken here also, right? So we are taking same assumptions. What are those assumptions? Ideal converter components, ideal converter components. What else? Operating in continuous conduction mode. We have still not defined it. We will do it most likely in next 1 or 2 video lectures. So these are the two assumptions that we have taken to find this expression and small ripple approximation, right? As and when required, we usually take that approximation also. So with this, we have found the average relationship. You can see that if the duty cycle is less than 0.5, then VO by Vin is going to be less than 1. And therefore, this would operate as a buck mode. And if duty cycle is greater than 0.5, VO by V is greater than 1, and this would operate in boost mode. Now, there are few things I would want you guys to do. First is find the output voltage ripple and inductor current ripple. Right? So you can find expression for both of these things. You can follow the same approach as we have done for the other DC to DC converters till now, right? Just follow the same approach and you should be able to get an expression for the output voltage ripple as well as for the inductive current ripple. So this, I want you guys to do it on your own. Then second thing is, I want you to find the output voltage upon input voltage for a resistance, inductor resistance RL, right? So what is this? This is resistance of inductor. So with RL included, go ahead, find the expression for VO by Vin the way we have found it for boost converter. And once you do that, you would realize that it's very similar in that sense that you would have a limit of how much maximum you can boost, and you would have a limit on the maximum duty cycle also, right? So go ahead, do this, and then find what is Vmax and what is Dmax. Third thing which you can do is that in boost converter, we have found what is the relationship between efficiency, what is the trend of efficiency with duty cycle, right? Only by considering RL, only by considering the resistance of inductor, right? Not considering other losses. So you can do that for this particular converter also by following the same approach.